Okay, thanks, Sarah. And now that Sarah has told you that I'm famous for making interesting and very high quality samples, I'm going to spend the rest of the colloquium telling you how you get really cool physics from low quality samples. So, as Sarah mentioned, I'm also department head at Penn State. And are there any undergraduates in the audience by any chance? Or? One at least. Okay, good. Okay. So the reason I'm asking is because as department head, I carry these two hats, right? I wear these two hats of being department head and also running my research program. And one of the things that I like to do when I give talks is to advertise what's going on in the department. So it's not just for undergraduates who might be applying to graduate school at some point, but also the graduate students here who might be interested in looking for postdocs, and postdocs here who are interested in looking for faculty positions. So please do spread the word. I'm going to just give you a few ideas of what's been going on. So I became department head in 2011, and I've been asked to do this for the next 5 years also. But in that time, we've done a lot of hiring at Penn State. So across the entire range of fields, from AMO, particle astrophysics, biological physics, condensed matter, gravitational physics, cosmology, and so on. So please tell your undergraduate students about our department. All these young people are looking for new people to join their graduate research groups. And so it's a very exciting time for us. A number of them have got prominent awards. We just got the Packard Fellow this year. We've had Sloan Fellows, various Young Investigator Awards, and so on. So having said that, I also want to advertise for those of you in condensed matter physics that at Penn State we have a fantastic facility for doing materials and nanoscience. This is the building that it's housed in. And we've got really good clean room space, all sorts of materials characterization capabilities. One of our big users, actually, of the clean room now is someone who does X-ray astronomy by launching rockets, and so on, who's a joint program between physics. He's also a physics faculty member. So if you're interested, again, for postdoc or graduate student positions, please look us up. And finally, again, for condensed matter physicists, we recently got funded by the NSF for a big NSF program. It's a user facility. I'm one of the co-PIs on this. And it's aimed at teaching a broader audience in condensed matter community how to grow samples, synthesized crystals of various kinds, focusing on two-dimensional materials. So please look up mip.psu.edu, and you'll see what this is, what the capabilities are. We are looking for users to come and take advantage of this facility. Okay, so having done that, let me just go on now to the outline of my talk. So I'm going to be talking about materials that are known as topological insulators, and I'll give you an introduction to what we mean by that. I'll then go on to talk about the effect of broken time reversal symmetry in these systems and show you some of the really cool new physics that comes out from doing something that's very fundamentally oriented. And it's still, these are going to be the kinds of physical phenomena that still only show up at very low temperatures. But they have a nice overlap between condensed matter physics and ideas that also, that were considered in generally in fundamental physics for quite some time. And then I'll switch gears in the last 15 minutes or so and go to the other end of the spectrum. So all these measurements are going to be done at very low temperatures, typically below 4 Kelvin, whereas the final part of the talk will be on trying to actually do something with these interesting materials. And these experiments are actually done at room temperature on a tabletop. And the reason for that is because we are interested in trying to see whether we can actually develop real applications. So let me begin with since this is a colloquium, just try to set things at a very beginning stage. You've all heard about the idea of the quantum Hall effect discovered by Klaus von Klitzing. And the idea was that if you take a two-dimensional electron gas and you put it into a magnetic field that's perpendicular to the electron gas, then you form Landau levels. And these Landau levels, in the presence of a small amount of disorder, but still long enough mean-free paths so that you can complete a cyclotron orbit, will give you these, when you measure transport in such systems, then I'm missing one more label here. It should be rho xx and rho xy. The longitudinal resistivity goes to 0 at certain points in magnetic field, and rho xy, which is the steps over here, this is the Hall voltage or Hall resistance, takes on quantized values. And then later on, Stromer and Sui and Gossard repeated this experiment in much cleaner samples and found that these plateaus, instead of simply taking integer values of h over n e squared, they could take on fractional values of h over e squared. So these two kinds of physics are entirely based on the formation of Landau levels, and we've been able to understand this in terms of edge states. So when you apply a magnetic field like this, then because of the magnetic field, the electrons that are in the bulk of the sample or in the middle of the sample are going around in orbits like this, but at the edge, they sort of make skipping orbits, and so your entire conduction is confined to these edge states. Now, what's interesting is that you can take samples of this kind, which are based on some standard material like gallium arsenide, or you can come to my lab and grow some weird material that no one else cares about. So these are zinc selenide 2D electron gases, and get the same degree of quantization. So this effect, the quantum Hall effect, is independent of details about the sample and the material. All you need is a two-dimensional sheet of electrons, and you need some amount of cleanliness to the sample. That's all you need, and a magnetic field, right? So one question is, why is it that this quantum Hall effect was so robust against details of the system? And we reached an understanding of this from a paper that Thouless, Komoto, Nightingale, and Denise published in 1982. And they argued that, well, this quantization of the resistivity, or equivalently the conductivity, because that's what theorists can calculate in a more fundamental way, the quantization of the Hall conductivity is related to some fundamental properties of the band structure, and they related it to to integrals of this sort, which essentially take concepts from topology and bring them into the realm of physics. And so the idea here was this integer n that characterizes the quantization of the Hall conductivity or the Hall resistance is related to concepts such as the Berry curvature or the Berry connection of the system that you're looking at. And so these are concepts that were quite abstract, and because they're abstract, they tell you that, well, the details of the system do not really matter. What matters is the topology of the system. And in this kind of language, one can characterize the vacuum that surrounds this sample by a Chern number which is equal to 0, and then you can characterize this quantum Hall insulator in the middle in terms of this Chern number which is equal to n related to this integral, and then in between over here you have these edge states. So this is the first time that this kind of a concept was really applied to physical phenomena in condensed matter physics, and has become a very powerful concept in our field now. Now, one of the questions that was addressed in 1988 by Duncan Haldane was, can you conceive of a system, a physical system, in which you can get quantization of the Hall effect without any Landau levels and without a magnetic field? Now, being a theorist, Duncan, of course, is free to let his imagination run wild as long as things are consistent with physical laws and mathematical rigor. And he came up with this very interesting idea that if you take what we now know to be a sheet of graphene, and you come up with some theorist's concept of applying some periodic magnetic field and so on, he could come up with a model in which he said that, well, I can imagine a 2D semi-metal in which a combination of inversion symmetry and time reversal symmetry creates a degeneracy at isolated points in the band structure, in the Brillouin zone, between the top of the valence band and the bottom of the conduction band. And he argued that if you break time reversal symmetry in such a system, then that opens a gap in this metallic system. And this gap is going to be characterized by a Chern insulator number, a Chern number in which sigma xy, which is the Hall conductance, is fundamentally quantized in units of E squared over H in zero magnetic field. Now, I recall being in Duncan's office while I was giving a seminar at at Princeton, not in, sometime after this, I think when I was an assistant professor at Penn State, and he spent half an hour explaining this idea to me, and I didn't understand a word of it. So I just totally ignored it. Besides, I said, I can never make a system like this, right? Now, much to my dismay, it turns out that I should have probably listened more carefully, because there were ideas that came up later on in which theorists like Shucheng Zhang and others said that, well, we can't really make the systems that Duncan was talking about, but there is a way to achieve this idea of having edge states in zero magnetic field. And one of the first concepts that they came up with was by looking at heterostructures. So these are layered semiconductor structures in which you take sandwiches of semiconductors, but you make the middle layer over here thin enough that you get quantization effects. Quantum confinement becomes important. And you play with the band structure in such a way that instead of having a band gap in the semiconductor, you get some states that cross this band gap. So these are states that are metallic, but the blue and red states correspond to not our recent election, but spins of different orientation. Okay, and using this kind of concept, they argued that one could make what's called a quantum spin Hall insulator, which is again characterized by some topological invariant. And this topological invariant is called a Z2 topological invariant. And experimentalists in Germany actually went ahead and made these systems. And they've been able to do measurements in which it's not quite quantized. So this is resistance versus some parameter which changes your Fermi energy or chemical potential. And they get some wiggles over here that are approximately in the range of what you would expect to be quantized. Okay? So there is some idea that now, without a magnetic field, one can imagine creating states that are edge states. But this is still not a realization of Haldane's idea, because time reversal symmetry is still obeyed over here. This had to go a little bit further in order to come, to get to the Haldane phase. And remember, the key idea of the Haldane phase is that you want to break time reversal symmetry, and that's what generates a Chern insulator. Okay? So we're at a stage now, as I said over here, where we've come up with some kind of two-dimensional system in which there are edge states that propagate without any magnetic field. But time reversal symmetry is still in place and working. So this field now moves on. And a few years later, there are even more ideas that come up with condensed matter systems, in which, again, this is Shucheng Zhang and others, but also Liang Fu and Charlie Kane. They came up with the idea that there are certain kinds of semiconductor crystal structures in which, because of the presence of very strong spin-orbit coupling and time reversal symmetry, the band structure has this form. So here is the conduction band, here is the valence band, here is a forbidden gap of energies, but in this forbidden gap, you get some states, you get some energy states that span this gap. And these energy states have a dispersion that is Dirac-like. In other words, the energy versus momentum, this is crystal momentum, has a linear form. So that's why we refer to it as a Dirac kind of dispersion. But as you go around momentum space, around this cone, you find that the spin and momentum are correlated with each other. Now, this is a bit of a, little bit of a simplification, because of the strong spin-orbit coupling, spin is not really a good quantum number. But nonetheless, if you look at the wave function associated with these states, you find that a particular spin direction dominates. So we refer to this loosely as spin momentum locking. And we draw arrows and so on, to represent what's going on there. But as you go around this Dirac cone, what it's telling you is that if you were to look in real space, that an electron propagating in one direction would have some preferred spin quantization axis. And if you reverse the direction of that electron, then that spin quantization, the spin would flip its direction. So these materials are now called three-dimensional topological insulators. They're three-dimensional because the crystal is three-dimensional. But the states now, the edge states that existed in this 2D system, at the edge of the sample, are now on the surface. So they're surface states, which are the equivalent edge states in this 3D system. And these are, again, characterized by some topological invariance and so on and so forth, right? So there are materials now that were identified as being, as the kind of materials that would host these types of states. And these have been made. These have been made by a number of groups, initially starting in Princeton and Stanford and at Tsinghua University and other places. People made bulk crystals of these materials. They then carry out an experiment called photoemission, in which you bombard the sample with energetic electrons, you look at with energetic photons, and then you look at the emitted electrons, and you measure the momentum versus, the dispersion, energy versus momentum, and you can map out the band structure. And this band structure then shows you the existence of these topological, of these Dirac states. And if you furthermore do an analysis of the spin of these electrons, you find that indeed, as you go around the Dirac cone, this is a plan view here of the Dirac cone, you find that these red arrows represent the direction of the spin. So using angle-resolved photoemission, the existence of these materials and these states was certainly established quite early and very, very quickly by a number of groups. Now, I got interested in this field roughly at this point where these bulk crystals were being grown and people had started making to some extent thin films in labs in China, and we got interested in using our method of synthesis to grow crystals of these systems, so make thin films of these systems. So the way we do it, and I'm not going to go into too much detail, is by using ultra-high vacuum chambers. So this is the lab in which it's done. We evaporate the various elements, and as we evaporate the various elements, we can monitor the surface by using electrons that are reflected off the high-energy electrons, about 15 kilovolts, that are reflected off the surface of the sample. And we can monitor diffraction patterns, but we can also monitor the layer-by-layer growth. It's sort of like playing atomic scale Legos, where you can monitor the growth of one unit cell. In this case, this is one quintuple layer. There are 5 atomic layers that are formed during these oscillations. We can then slice the samples and use electron microscopy to look at the structure of these samples. This is some topological insulator, bismuth selenide grown on a superconductor, niobium diselenide, and you can make reasonable structures, right? So we've been able to grow these kinds of thin films on a variety of substrates that are all listed over here. And unless you're a condensed matter physicist, you don't particularly care what all these substrates are. But just what I want to get across is that we can combine these materials with magnetism and superconductivity of different kinds of materials. Okay. Once you make samples of this kind, you want to find out whether these surface states exist on the samples. And since we can't do it in our own chamber, in our own facilities, we've been collaborating with Zahid Hassan at Princeton University. And the way we do this is that we take our samples, we passivate the surface, we protect the surface with a special kind of layer. It's a layer of selenium. And they can then take this into an ultra-high vacuum chamber, evaporate the selenium, and they can see very clean energy spectra that are corresponding to these surface states. Furthermore, by using a gold foil, which serves as a Mott spin detector, they can do a spin-resolved experiment where they map out the spin as a function of energy and momentum in these materials. Okay? So there are a variety of defects in these samples that occur when they are grown by the method we use. And one of the typical defects is called the selenium vacancy. So this is a missing selenium atom in the crystal structure. And what happens is that donates electrons, and because of that, the chemical potential in the samples is typically far up in the conduction band in the as-grown samples. And this leads to some difficulties that I'll explain in a minute. So once you start growing materials of this kind, you can essentially do band structure physics. So you can map out how the wave functions and how the energy states behave as a function of quantum confinement. So for example, imagine that you take, you can ask yourself, what happens if I take a crystal that is extremely thick, right? On all the surfaces of the crystal, I have these Dirac states. But as I start making the crystal thinner and thinner and thinner, at some point, the wave function of the Dirac states on the top and bottom surfaces will start coupling to each other. And when they couple, they hybridize. And when they hybridize, you open up a gap. So what happens is that as you go from samples which are about 7 nanometers, so QL refers to quintuple layer, that's a unit cell, it's about 1 nanometer. As you make a thin film thinner and thinner, you find that this point over here, the Dirac point as we refer to it, opens up, it's disrupted, and you get an energy gap over there. And that energy gap is because of the hybridization of the top and bottom states. We've also done measurements, using samples like this of the spin polarization by using the Mott spin detector. And what Zahid and his students and us we were able to do is to map out how the net spin polarization varies as a function of the thickness of the films. And it's very interesting that you can do this sort of tabletop quantum mechanics, Dirac physics, by using equations that are effectively the relativistic Dirac equations describing these energy states, and map out everything, how do the wave functions behave, how does the spin polarization behave. And what you find is that as you open up a gap, as you hybridize the top and bottom surfaces, you start quenching the spin polarization in these samples. And this becomes an important aspect of applying these materials for devices in a field called spintronics, because as you change your chemical potential, depending on the design of the sample, you could in principle vary the spin polarization that you're using in your devices. So it becomes an interesting knob that you can play with. Now, as I mentioned, one of the problems that we face in making these thin film samples by the technique that we use, molecular beam epitaxy, is that there are these selenium vacancies that are formed. So these are not perfect crystals or great materials, as Sarah was mentioning. They are riddled with defects. And the prominent defect is really the selenium vacancy. Now, what one would like to do is do measurements in which you're dominated in transport, in electrical transport, by these surface states, and you don't have conduction anywhere else. But with these selenium vacancies, it's a problem. So what we decided to do, and this was something that was first done by a group in IOP in Beijing and Tsinghua University, the idea was that when you grow this material or this material, you have these vacancies, and they're typically doped N-type. In other words, the carriers are electrons. If instead you grow this material, then it turns out that the defects are such that it's predominantly p-type, and the carriers are holes. So imagine that instead of doing this or doing this, you make something that's a combination of the two, and then what happens is that you start getting films in which the chemical potential is in the gap, right? In which you have a low carrier density. Now, if you now, on top of this, grow the sample on a particular kind of substrate, something with a large dielectric constant, then you can effectively make a capacitor by putting a metallic contact on the back of the substrate. So you make a capacitor in which you can change the carrier density in your capacitor, or you can change the charge on your plates. And so this is called gating. And as we gate the sample, so this is the voltage that you apply. The red curve over here is the resistance of the sample, or the resistivity. And the blue curve is the Hall effect. And you can see that you take your resistivity through a maximum. This is where the Dirac point occurs. And at the same time, as you look at the Hall voltage changes sign because you go from electrons to holes. So despite the fact that these samples have these defects, you can grow samples in a form that allows you to change the chemical potential such that you're dominated by the surface transport, and you're not having a large conduction channel that is in the bulk. So having introduced this idea of topological insulators, let me now go on to discuss how we can break time reversal symmetry and look at what is called the Haldane phase in a more general sense, and called the quantum anomalous Hall effect in the context of topological insulators. So the idea here is, regardless of whether in condensed matter or not, anyone who has done a course in relativistic quantum mechanics will recognize that if you look at the Dirac equation in 2 dimensions and you write it down in this way, then clearly if you introduce a mass in that equation, you automatically break time reversal symmetry. So the converse is true in the case of a 3-dimensional topological insulator, because just as you have a Dirac equation like this for free electrons, in condensed matter physics, we have a Hamiltonian that looks like this, where this is the crystal momentum. And now in this Hamiltonian, if you break time reversal symmetry, what happens is that you introduce a term that looks just like this. So in other words, it looks like a mass. And what happens is that instead of this Dirac point, you get a gap opening. Now this is fundamentally different from the hybridization gap. This is created by the breaking of time reversal symmetry. And one question is, can this effect be observed in experiment? People have tried to do this by breaking time reversal symmetry by introducing magnetic ordering into a sample. Now, there are many implications of this, and I won't go into them, but they range from the very fanciful, things like creating axion fields in condensed matter, to creating an artificial magnetic monopole, for example. But I'm going to go to the one that's actually been realized. And again, it came from a theoretical idea, but it's one that we were able to realize, we in the sense the community was able to realize in experiment. And this was a paper by Shucheng Zhang's group in 2010. And they argued that if you take a three-dimensional topological insulator and you make it ferromagnetic, then you will, as I argued on the earlier slide, you will go from a situation like this to something like this. But they argued that in this gap, you will actually get a state that's going to be no longer this helical Dirac state that we talked about on the Dirac cone, but rather it's going to be a chiral edge state. So this will be like the Haldane state. It's something that propagates around the edge and has chirality to it, right? But without any Landau levels, without any magnetic field. And when this happens, the Hall conductance should take on values of E squared over H, and the the longitudinal conductivity should go to 0. Remember, this is a two-dimensional system, so you can have the longitudinal resistivity and the longitudinal conductivity go to 0, because they're related by this very simple, the conductance matrix, right? So this is known as the quantum anomalous Hall insulator. And if you want to picture it in your mind, the way you can think about it is that in this case, you have surface states that are spin momentum locked. So this is the way a current would propagate with a predetermined spin. But when you now break time reversal symmetry by magnetic doping, you now get this state that propagates around the edge. I've drawn arrows to represent the spin of this edge state, but that's, I think, that's an oversimplification. There's a calculation done by my colleague at Penn State, Xiaoxing Liu, that shows that, he tells me, Nitin, this arrow is wrong. It can be in any direction. It depends on the circumstances. But nonetheless, you can get this propagating edge state. So we can make these samples. We make the samples by taking one of these crystals that we are typically making in thin film form, and we introduce some magnetic dopants. So these are typically transition metal elements like chromium or vanadium or manganese or iron. So here is an example of some transmission electron microscopy. This is a cross-sectional view with electron microscopy where you see these quintuple layers being formed. And again, you have to be careful. When one shows electron microscopy images like this on this very limited spatial range, it looks like these are extremely high-quality samples, but they are not. This is just a tiny slice of an extremely disordered sample. We do have, we can map out the distribution of the magnetic elements in this. And where is chromium? Chromium is somewhere here. To the extent possible with our current electron microscopy, we don't see obvious signs of any kind of, a clustering of the chromium into metallic clusters and so on. This is a problem that has plagued some of this field in the past, but it doesn't seem to occur here at any kind of length scales that matter. So they look reasonable, these samples. They're not the best, but they're reasonable. Now, do we break time reversal symmetry? Well, if you're breaking time reversal symmetry, you should see evidence of ferromagnetism. What does that mean? That means that if you sweep a magnetic field to some high value, bring it back to 0, and then reverse the field, if you're measuring some property that is characteristic of the alignment of the spins, then you should see a hysteresis loop. And that's indeed what we see. You see the hysteresis loop in a squid magnetometry measurement when the magnetization is pointing out of plane. If you put the magnetic field in plane, then the hysteresis loop goes away. That tells you that the magnetic moments are pointing out of plane. You can do a similar measurement by using optical spectroscopy. So this is just to show you that this looks like a run-of-the-mill ferromagnet. Now, this is what led to the discovery in Tsinghua University and IOP by Qikun Shui and his then student, Chuezu Chang, who is about to join our department, incidentally, in January as an assistant professor. And they found that if you made such a sample and you tuned the chemical potential, so you apply a voltage to the back of the sample, using this capacitor technique I talked about, and then you can adjust this chemical potential. When the chemical potential goes into that gap that has been opened by the breaking of time reversal symmetry, then at very low temperatures, rho yx, which is the Hall resistance, is quantized precisely to h over e squared. Now, when I say precisely, in this initial experiment published in Science, it actually wasn't precise. They weren't too careful about trying to show that it was precise. And in fact, what they found was that the resistivity of the sample never actually went to 0. It looks like this on the scale, but it's not. It's still sizable. But since this initial paper, which is a seminal paper, it's the seminal discovery of this phenomenon, a number of groups, including mine, have shown that this is indeed reproducible. It's real physics. It's not some accident. And you can make samples that show these properties. And this has come to be known as the quantum anomalous Hall effect, and in many ways is actually the first physical realization of this phenomenon that Haldane predicted. Although, of course, not at all in the form that he envisioned, right, for somewhat different reasons. So one important question that arises now is, there are people in this audience like Sarah and others who study magnetic materials. And one important question is, OK, so Nitin, you've made a ferromagnet. What is the nature of this ferromagnetism? Is it a conventional ferromagnet with long-range ferromagnetic order? What does it look like? So we're very curious about this. And so I approached Eli Zeldov, who's a friend of mine in Israel. He has this terrific technique to image magnetic systems by using a nanosquid. So this is, he basically puts a loop of niobium at the tip of an optical fiber. And so this loop of niobium has a diameter of something like 200 nanometers. And then he can scan it across a sample, while at the same time, they can measure the transport. So here is this anomalous Hall effect, not quite quantized because we're at 250 millikelvin, we're at too high a temperature, but it's reaching there, And then here is the longitudinal resistance. Now, what his squid measures is variations in magnetization. So he's seeing the fringe fields that are created by inhomogeneous magnetization in your sample. So if you have domains, for example, you'll see the magnetic domain. So let's start at this end over here in the hysteresis loop, and this is the kind of image he gets. Okay? Now, you go over here where the magnetization is just starting to switch, and you start seeing that red and blue regions are opposite directions of magnetization. You start seeing that this magnetization is starting to switch. And if you now go ahead and saturate the magnetization, surprisingly, it looks sort of like this, where there are some domains still that exist, even though you've swept all the way here. And when you go back, oops, went the wrong arrow. And when you go back to this state over here, which is on the other side of the magnetic field axis on, just the negative of this positive over here, you find that you get an image that again looks like this. And if you look very carefully, you'll see that for every blue region over here, there's a red region over here. So in other words, the way this magnetization is switching is not by the growth of domains and the propagation of domain walls, but rather by a very localized kind of switching of the magnetic domains. And what it appears to be is that, when I told you that my samples, that these samples, not just mine, but everyone else in the field who grows these materials, are highly defective, we believe that what's happening is that, the magnetism is accompanying this magnetic disorder and this structural disorder, and the domains are strongly pinned. And so what we are seeing is strongly pinned magnetic domains that are constrained to switch locally without propagating domain walls across the sample. Okay? So despite the fact that you have these samples with defects, structural defects, the electronic disorder is also quite high. The mean free paths are typically only about 30 nanometers or 50 nanometers, somewhere thereabouts. If you go to very low temperatures, we find that the quantization of Rxy is extremely precise, 4 parts in 10 to the 4. So despite the presence of all this disorder, you find that you can precisely quantize the effects, the phenomena associated with these edge states. And in fact, if you go and look at the longitudinal resistance, you find that Rxx goes down to fairly low values, a few ohms essentially, in these samples. And again, this is despite the presence of this disorder. So note that the mobility is just something like 150 centimeters squared per volt second. Okay. Now, I told you that there is a gap that is opened up by the breaking of time reversal symmetry. So one question is, what is the size of this gap? And here is another puzzle. The magnetic ordering that we see in these samples typically occurs at about 20 Kelvin or thereabouts. So these are the samples that show the best quantization. So 15 to 20 Kelvin. How do you measure the gap? Well, the way you can measure the gap is that you can go and look at where Rxx has reached a minimum, okay? And then you can measure that as a function of temperature. And what happens then is that from this dissipationless state, you're getting thermally activated to transport that is dissipative. And so if you measure the natural log of the longitudinal conductivity plotted as a function of 1 over temperature, you get activated behavior over some range of temperatures. And from this activated behavior, you can pull out a gap. So despite the fact that the ferromagnetic ordering temperature is of the order of 15 Kelvin, the gap is very, very small. It's only of the order of 150 to 200 millikelvin. So this is quite surprising. We don't quite understand it. We've been talking to our theorist friends to get some idea, and this question is still open. Why is there such a big discrepancy in the energy scales of the ferromagnetic ordering and the gap that we are creating over here? I think it's still not a resolved question. Now, one of the questions one might ask is, at these low temperatures of 10 millikelvin, where you get this very precise quantization, how is this magnetization reversal taking place? Is it still dominated by this very local reversal of magnetic bubbles that I showed you, or is it something else? We cannot image at these temperatures in a dilution fridge. We just don't have a technique to do that. And so instead, what we decided to do was to see whether at these low temperatures, from below 200 millikelvin, how does this magnetization reverse? And we'd want to look at this very, very carefully, simply through transport. So this is work done in collaboration with Fuanong at Princeton, and a brilliant postdoc, Minhao Liu, who, by the way, is on the condensed matter physics job market this year. The guy is fantastic. He decided to look at this switching process, this step over here, extremely carefully. Okay? And what he found was quite surprising. When he sweeps the magnetic field extremely slowly, he finds that once you are at temperatures which are above that base temperature at which we were seeing the precise quantization, you find that the switching is no longer some kind of smooth process, but occurs in steps, very, very sharp, discrete steps. And these discrete steps are limited in resolution by the magnetic field sweep that you're doing. So this is very, very puzzling. We started wondering what this is due to. If you work in magnetics, the first thing that comes to mind is that this is possibly some kind of domain wall motion where you're getting domains that are pinned, and they suddenly they get liberated, they jump, and then they get stuck in some minimum potential, then they jump again as you sweep your magnetic field. And that as you raise your temperature, all this should be somehow thermally activated, right? So there should be a simple classical kind of explanation for this. But it turns out that that doesn't at all make sense. It does not jibe with what we measure experimentally. So the way to characterize this data is to look at 2 parameters. One is that at any particular temperature, you can look at the height of the jump, right? The height of the first jump that occurs. That's the first sort of liberation of this domain wall, if you want to take that picture. And the second thing you can ask is, what is the field at which this first step occurs? Now, if you plot these 2 parameters as a function of temperature, you find that the jump magnitude of that first step increases to h over e squared, So essentially at 100 millikelvin, there's just one jump where you go from minus h over e squared to plus h over e squared, right? It's a dramatic jump like that. And then after that, that jump magnitude decreases, and it vanishes roughly where that energy gap is, so around 150 millikelvin. If you now measure the field at which the first jump occurs, then that field turns out to increase monotonically with increasing temperature with no particular non-monotonicity, just a steady increase in temperature. Now, these are the two parameters we have to play with, and this is the temperature dependence that we have to play with. So you can start asking yourself, well, can this be explained in some simple classical model? And you can try developing some simple classical model in which you say to yourself that, well, when I bring my field from negative values through 0, and I cross the 0 value of magnetic field, I'm going to be in some metastable state where these magnetization moments, the moments are still pointing in the direction that the magnetic field was earlier. And then as I start approaching this jump field, then I'm going to nucleate some bubble of magnetization, and that bubble of magnetization will grow, right? So you can try to analyze this by using a simple two-dimensional model, an analogy in some sense, in which the surface tension of a bubble is connected to the exchange energy in the problem. And you can try to then develop a simple model in which you try to understand how the expansion of this bubble might be explained in a classical sense. And the way to think about it is that imagine that the metastable state of the system is in some state of magnetization over here, and then here's the true ground state, and the question is, how does the system go from here to here? Is it simply thermally activated, or is it something else, right? And if you just follow through in this kind of argument, then you can easily argue that, well, the rate at which this process is going to occur is going to be such that if you are using this field, which initiates the jump, as a measure of this, activation process, then there is no way to explain this process on a purely classical way. So in other words, Hj, that jump field, cannot be increasing as you increase your temperature. The argument would go that it has to actually decrease, and we are seeing just the opposite. So the picture that we are developing here is one that doesn't seem to make sense in terms of a simple classical argument. Now, at this point, being experimentalists, we sort of throw our hands up and start using words. And so there is no rigorous explanation that we have of the phenomena that we are seeing, but we are speculating at this point that at high temperatures, we get this reversal of these little magnetic bubbles in a completely uncorrelated way. But as we go to low temperatures, we speculate, and I'm emphasizing the word speculate, that we may be seeing a process in which the state of this system actually tunnels through the barrier that you have and goes into the true ground state. And this is an analogy with ideas that have been developed in completely different contexts, but we would like to see if we can develop at least a rigorous picture of this by, so we're talking to some of our theorist friends to see if one can put this on some more rigorous footing. But being experimentalists, even if we come up with a speculative picture like this, at least we have to have some evidence that there is some evidence for a macroscopic reversal of the magnetization. In other words, something where the ground state of this system is reached in a dramatic and a way which involves large length scales. And we believe we do have evidence for this. So here's a sketch of the samples that we are measuring. Just to give you some idea of the length scale, the typical spacing between these contacts over here is about 500 micrometers, or half a millimeter. Okay? What we do now is, as you are measuring the sample, you measure, for example, the Hall voltage over here, this pair of contacts, and this pair of contacts simultaneously as you sweep your magnetic field. And what you find is that this Hall voltage jumps, or this resistance jumps first, and this resistance jumps at a later stage, at a higher magnetic field. Similarly, if you measure this voltage and this voltage simultaneously, then you find that one of these voltages jumps up and the other voltage jumps down at the same time. Now, this is rather odd, and the only way that we can explain it is by using a simple model. It's a Landauer-Buttiker model in which we imagine that there is a very simple structured domain wall that's sweeping across the sample. And here are the results of this modeling. So indeed, if we assume a simple model like this, not of uncorrelated switching of little magnetic bubbles, but rather a macroscopic change of the magnetization across this large millimeter scale sample with a single domain wall, or at least some simple structured domain wall, sweeping by, we can in fact reproduce this kind of phenomena that we see in experiments. In other words, Rxx jumps up and down for opposite contacts, and Rxy has a lag in the field at which the Rxy switches. Now, again, this is, as I said, it's just experimentalists trying to interpret the data without much rigor at this point. So what is the outlook for this quantum anomalous Hall effect, or the Haldane phase? Well, there are some important questions that arise. First of all these measurements have been done at dilution fridge experiments. Dilution fridge temperatures. So can we increase the temperature scale for the observation? There's a group in Japan, Tokura's group, that has recently demonstrated that they can actually see the effect up to about a few Kelvin. They've done this by using some materials magic that no one quite understands why it works, even though they have some, they have some speculation as to why it works, but they've been able to make samples like that. But can we take it much higher? It's not clear how do we increase that temperature. What is the spin polarization of these edge states in the quantum anomalous Hall effect? It's not at all clear what that spin polarization is, although there is, as I mentioned, a theoretical calculation recently that suggests that it can be anything. But the question is, how do we measure it? That's a really important question. The next question is, just as in the case of the integer quantum Hall effect, as samples became cleaner and the effects of electron-electron interactions came in, we saw that there were more complex fractions, more complex quantized plateaus that were formed. Is there any way to get such rich behavior in these kinds of samples? It's not clear how to do that. And finally, there is a lot of interest in trying to couple these edge states with superconductivity for reasons that I won't go into, but they're related to ideas that are being pursued here by Sergei Frolov and others in the context of Majorana states. So there's a lot to do here. Now, in the remaining 10 minutes or so, I just want to, 10 or 15 minutes, I hope, I just want to go over another set of experiments which are in a completely different regime. So everything I've shown you so far with the quantum anomalous Hall effect was at dilution fridge temperatures and low temperatures. But can these materials ever be useful? And the question is, to make those useful, you need to have phenomena that occur at room temperature. So one of the interesting aspects that drove me towards these topological insulators is a concept called spin transfer torque. So this is physics that you may have heard of from earlier colloquia. The basic idea is that imagine that you have some magnetized material. So this is a ferromagnet, and imagine that you send a spin polarized electron through this ferromagnet. Without going into too many details, the essential idea is that sort of because of conservation of angular momentum, as this electron has to go through, if it's misoriented from this magnetization, then it exerts a torque on this ferromagnet, and the ferromagnet will experience a precession, or it'll get tilted because of this passage of this spin polarized electron. So the reason why people are interested in this kind of phenomenon is because it leads to technologies that are quite interesting. So one of these possible technologies is a magnetic random access memory in which you use the spin transfer torque to essentially to flip a magnetic bit by using structures such as this. And it's a technology that is believed to be competitive with current memory technologies. And it has certain advantages, like it's non-volatile, it has low standby power, and it can be quite robust to many, many cycles of usage. So because of this, there are people like Dan Ralph at Cornell, but also Sarah over here, and Jimmy Zhu and so on, who have been working on the idea of using this spin transfer torque effect to make new kinds of magnetic memory technologies and even logic-based technologies. So one of the ideas that Dan Ralph and his group demonstrated some years ago was that if you take a metal like tungsten, so tungsten is something that has a strong spin-orbit coupling because it's a heavy element, and you flow a current in tungsten, then what happens is that because of a phenomenon known as the spin Hall effect, you get a spin current which is generated in an orthogonal direction. Okay? So you flow a charge current over here, but you get spin polarized electrons going this way. And if you now have a magnetic system on top, it turns out that instead of using a magnetic field to change the state of a magnet, you can just use a current. Right? So this is a hysteresis loop, but there is no magnetic field here. This x-axis is a current that's being driven through the sample. And the key thing that matters to people who want to make devices is what is the figure of merit of such a device or such a material. And the relevant figure of merit is something that is called variously a spin Hall ratio or a spin torque ratio. And it's essentially a ratio of the spin current density to the charge current density normalized by fundamental units of angular momentum and charge. So this kind of phenomenon has been now studied in many, many systems, particularly heavy metals. And the question is, can we use these special Dirac states on the surfaces of topological insulators to have an impact in this field? And the question, of course, is, well, come on, you have a Dirac cone. So here is a view of this Dirac cone from above. And this is without any drifting electrons. If you now apply an electric field and you shift this Fermi disk in some direction, then you're going to be dominated by electrons of, the colors here correspond to spin. So you'll be dominated by some spin polarized electrons. And can that be a very efficient way to generate a spin torque? So in other words, what is the value of this theta? What is the value of this figure of merit? So we undertook this experiment first in a collaboration with Dan Ralph at Cornell. And it came off, it's an experiment that really went off in a direction that there were no really predictions over here. So in Dan Ralph's group, what we did was we made bilayers of permalloy, which is a ferromagnet, with bismuth selenide, which is the topological insulator. You then drive an RF current through this combination, through this bilayer. And you can monitor the precession of the ferromagnet. So you basically apply a magnetic field at some angle. You set the magnetization of the ferromagnet into precession. And you monitor the precession by using a DC voltage technique. So it's a very simple idea, which is complex in its details, but the measurement itself is basically measuring a DC mixing voltage in this direction as you sweep a magnetic field. And as you sweep your magnetic field, you take this precessing ferromagnet into resonance, right? It has a certain precession frequency, which is determined by the magnetic field. And when that precession frequency matches the frequency of the RF current that you're driving through, you get some resonance effect. And if you measure this mixing voltage, you get a curve which is a mixture of an antisymmetric and a symmetric signal. Now you can analyze this data, this mixing voltage data, and from it you can pull out this parameter theta. So you can effectively figure out by fitting data of this kind what is the spin to charge conversion efficiency. Okay? So I'm simplifying a complicated story into one slide, but basically the idea is that you just deconvolve this curve into two components, and then by using various fits and parameters, you can pull out what this parameter is. So the bottom line is that if you plot this parameter, so here in the table is this efficiency theta parallel given for different kinds of metallic systems, and then for bismuth selenide, you find that the value, the efficiency that we get for this process in bismuth selenide is quite a bit higher than what you see in metallic systems. Now there's a word of caution over here, and the word of caution is that in this bilayer, remember you have two conductors which are in parallel to each other. It turns out that the resistivity of the metallic ferromagnet is much higher than, conversely, the resistivity of the bismuth selenide is much higher than the resistivity of the metallic ferromagnet. And so most of the current flows through this metallic ferromagnet. And that makes the analysis of this data somewhat complicated, and that's what generates this large error bar in this case. But the data are quite impressive because this occurs at room temperature, and you get a parameter value which is very, very intriguing and promising. But the problem, of course, is that it would be better to do this experiment by using an insulating ferromagnet rather than using a metallic ferromagnet. So this is something that my postdoc has recently done. We use a ferromagnet. It's actually a ferrimagnet, to be accurate, which is completely insulating. We then deposit this topological insulator on top, and we do a measurement that is the converse of what Dan Ralph was doing. So in this case, what we do is that we drive this ferromagnet into precession by using a magnetic field, but then we measure what's a voltage that's generated in the topological insulator. This is a process which is called spin pumping. And as you sweep your magnetic field, as you measure a voltage, you get these resonance peaks that correspond to the ferromagnetic resonance of the ferromagnet. And by analyzing this kind of data, you can pull out the spin to charge conversion efficiency. And we can now measure the spin to charge conversion efficiency. This is put in units that I'll explain to people in detail later if you're interested. But we measure it as a function of the thickness of the topological insulator. And what you find is that as you change the thickness of the topological insulator from a nanometer to something like 60 nanometers, you find that that spin to charge conversion efficiency plateaus just as you reach a thickness where this Dirac point becomes intact, right? So what we see is a clear correlation between the formation of the Dirac cone and the stabilization of this spin to charge conversion efficiency. And we believe that because of this correlation between what's happening as a function of layer thickness and what we know in the RPES is happening to the band structure as a function of layer thickness, we believe that what we are seeing here is clear evidence for spin pumping from the ferromagnetic insulator into the states of the topological insulator. And in this case, we have absolutely no artifacts that are due to conduction through a parallel layer or anything of that sort, right? So we believe that this is the way in which we can actually try to systematize what's going on in these types of materials. So what is the outlook for what I call now topological spintronics? And it all boils down to one thing. It all boils down to whether this spin momentum locking in the topological insulator surface states can be efficient enough for our friends in the engineering department to be interested in it. It's still not clear, publications in Nature or whatever notwithstanding, it's still not clear that this is the case. Because in the end, what's going to matter is whether one can make complicated devices that have been proposed where one substitutes a topological insulator instead of a heavy metal, and whether you can actually make this thing, make this device work at low enough power with high enough efficiency to be interesting to the device community, okay? So it's, I've tried to give you a very superficial but, broad-ranging overview of what I think is a really, really exciting field. I hope I've been able to show you that we can go from very fundamental ideas in physics, things like, breaking time reversal symmetry, Dirac states, and so on, all the way up to materials and phenomena that we think might be interesting for a technological impact. And here are all the people who have contributed. At Penn State, I have a really good group of students and postdocs who have been carrying out synthesis and transport measurements, and a really fantastic theorist, Xiaoxing Liu, my colleague, and then a number of other people who've been collaborating with us in helping us understand these fascinating materials. So with that, let me stop and take questions.